And this is the 20th video in a course on single agent search. This video is a continuation of the previous video. The previous video looked at how we can do external memory search and looked at explicit memory representations. And so it looked particularly at the problem of duplicate detection and looked at sorting-based duplicate detection, hash-based duplicate detection, and structured duplicate detection. And in this video, we're going to be looking at implicit state spaces. And we're going to be looking at particularly doing a breadth-first search through an implicit state space. And we're going to be looking at a couple of different approaches. And so let me just show you the model that we have of these state spaces. So if you haven't watched the previous lecture, I'm not going to go through some of the introduction material in this lecture. It might be good to at least do the beginning of the previous lecture to get some of that introductory material, because this is really continuing where that one leaves off. But the idea here is now I'm going to have my entire state space sitting on disk. So I'll draw that as this is my platter, my spinning disk. And this is my entire state space where every state in the state space has exactly one memory entry. And so this is on disk because it's too large to fit into memory. And the idea is I'm going to have a portion of memory which is much smaller than what is fitting on disk. So I'll draw a little old RAM card here. And so that would be like an old piece of RAM. And so we can see that we can fit some fraction of the state space into memory, but we cannot fit the whole state space into memory at once. But we have every state sitting here on disk. And so when we think about these implicit state space representations, we don't necessarily have quite the same problem of duplicate detection that we had when we wanted to do the search in the previous approaches. And so we're going to look at two approaches that sort of follow sort of two ends of a spectrum on approaches to doing search. And these are applicable not only to a breadth-first search for single agent search here, but we also have some work. It's not published yet, but it's hinted at in some literature, and it'll be coming out at some point, that describes how to do this for games as well. And so these ideas are really related here. And it's actually really important that these aren't, that there's some missing things in the literature that connects together what's being done in games and what's been done in the single agent search space. And what we're going to look at, the first approach is, we're going to look at two approaches today. One is called 2-bit breadth-first search, and the other one is called right minimizing breadth-first search. And these basically give us two ends of a spectrum of how we're going to deal with a question which is related to duplicates, but it's actually related to the question of how do I handle the work that I need to do when I'm expanding states. And we're going to take advantage of some properties here. So the 2-bit breadth-first search there's actually many interchangeable portions of these algorithms. And so the 2-bit portion here is actually something that can be used in the right minimizing portion. The right minimizing is something that has to do with, they both actually have to do with expansions. So 2-bit breadth-first search is actually trying to minimize expansions. And right minimizing breadth-first search is trying to minimize I/O. Okay, so these are two different approaches, but as I said, many of the different pieces that are being used here could be used for both of these. And so I'm going to sort of give the pieces that are a little bit independent, and then we'll talk about the structure that's related to both of them. So the 2 bits of breadth-first search is interesting. So this is a 2-bit search. And the 2-bit search has to do with the fact that if we think about our search, what do we have? Every state actually goes through 4 phases. Initially, states are ungenerated or unseen. And at this point, we've never seen them. We know nothing about that state. And then at some point, the first thing that's going to happen to a state is it's going to be generated. And when it's generated, that means it's something that's going to be expanded, in a search in particular. It's going to be expanded into the next layer. Okay, so it's been generated, but it hasn't been expanded, so it belongs in the next layer. And once I've finished a previous layer, that next layer is going to become the current layer. So it could be going from the next layer to being the current layer, which is now it's about to be expanding these states. And then once I've done this, it goes into being a previous layer or expanded. Okay. And these are the 4 phases that every state goes through as it's being searched. And if we think about that, given these 4 phases, this is all we have to keep track of in order to do an entire breadth first search. And if we want to do this, then if we look at this, given that there's 4 stages here, that means that it only requires 2 bits to store the stage of the search. Okay, so the stage is, we can call unseen to be 0, next layer would be 1, current layer is 2, previous layer is 3. Whatever we're going to use numerically for representing these, it doesn't matter. The point is we only need 2 bits to store them because there's only 4 states that a stage is in. And remember that an implicit state space here, any particular state inside here, I don't have to store the state itself. All I have to store is actually the data for that state, which in this case is going to be 2 bits. So 2-bit breadth first search is named after the fact that it uses 2 bits to mark down that a state goes through the layers unseen, next, current, and then being previous, or ungenerated, generated, expanding, and then expanded. And so what we can do is we can design a breadth first search around this process where we just keep 2 bits per state, and we keep track of this. Now, there's another thing that we could do is we could actually use a modular representation. And a modular representation can actually do the same thing. And a modular representation is what is being used by the right minimizing breadth first search. But again, there's nothing specific, like this is something that really is interchangeable between the 2-bit breadth first search and the right minimizing breadth first search. But the modular representation basically says I'm going to use k bits. K has to be greater than or equal to bits to store the depth of a state. Okay, and this idea actually was originally, well, okay, this is an older idea. In fact, what you can see is if I want to store all depths of a state space, you can use 1.5 bits to do this. And this is a way that was used to compress heuristics. And so we haven't gotten to this, but there was some work that looked at this. If you think about something like the final depth, in practice, what you really only need is the previous depth, the current depth, and the next depth. And if you use that, then if you give me a state, I can look at the states of the previous depth, look at the states of the previous depth, and I keep following the states of the previous depth. Eventually, I'll get to the start state or to the goal state, depending on where you start, but the initial state, and that'll tell me the depth of that particular state. So in practice, to store a final result and actually store all depths, I only need 3 possible states here, which I can do in 1.5 bits. Or 1.6 bits, and so that's a nice idea. But if I'm actually going to be doing a breadth first search, I need to be able to mark the states that I've never seen before. So we're going to need some more bits to do that. So I can use any number of k greater than or equal to 2 bits to store the depth of a state, and you basically store modulo 2 to the k. There's a caveat here that because we have to keep this ungenerated states, we're going to reserve 1 value to be unseen, and then every other value is going to be stored as a value modulo 2 to the k. There's 2 to the k minus 1 is really what's going on here. And that's going to allow us to store, like, is this the current layer, the previous layer, the next layer? And that's the same as recording, unseen next layer, current layer, previous layer. But the point would be here is if you have a state space that maybe only has, if I have only, let's say, depth 32, then I could use 5 bits per state instead of using 8 bits per state, and I might be able to significantly reduce the amount of memory that I need. Or I could use 4 bits per state, even if I have depth 32. And then when I get a depth, let's say I get a depth 7, then it's either depth 7 or it's a depth 7 plus 15 would be 22. Something like this. So we can use a modular representation, which in the end will allow us to extract out what the actual depth of a state is. Or we could think about a 2-bit search where we actually just progress states. This is unseen, then it becomes a value, which means next, it becomes the current, and then becomes previous. And all states become previous by the very end. And then I can't distinguish between those states because they're all previous. So there's some trade-offs here. And if you use a modular representation, you can end up re-expanding states because you can't tell. You won't necessarily know for a particular value if it's where it stands, but practically speaking, we're going to get we'll get something like the same results here. If you want more details on that, you can look at the Right Minimizing Breadth for Search paper, and that does describe the way that this can be done and describes the trade-offs in detail. But anyway, we're not worrying too much about those things because generally speaking, the idea is that we're going to have some low-level representation, which is going to allow us to do a breadth first search. And whatever it is, that's aside of the details. What we're thinking about is this question of, do I want to minimize node expansions or do I want to minimize I/O? And we'll look at that algorithmic difference. Okay, so the next thing that's going to happen at a high level, and again, there's a number of slightly different ways that this could be done. But generally speaking, what's going to happen is we have this large implicit state space here. And in order to do a breadth first search, what we want to do is we're going to divide the state space up into what we call buckets. And so the idea here is I'm going to say, well, look, all of these states here, they're one bucket, and they're going to correspond to the number of states that I can store in memory at one time. So I might break my state space up into, a large number of buckets. I might break them into a smaller number of buckets. Maybe I only need 2 or 3 buckets. It's going to depend on my state space and other properties like that. And these algorithms are going to have some slight differences that might change how I want to break these down exactly. But the idea here is I'm going to break these up in a way that allows me to store, let's just say this is our last group right here. And the idea that I want is that one group of these states here will fit exactly into main memory. Here we have disk. So disk has the full state space. And we have main memory, which is going to have one bucket. I call this a bucket, which it just corresponds to the way that we've broken up the state space into these separate pieces or separate buckets. And the idea of both 2-bit breadth first search and right minimizing breadth first search is that we're going to take one of these buckets, we're going to load it into memory, we're going to process it in memory, and then we're going to generally write it back out into disk. Okay. But so this is the general idea. We have the entire state space sitting on disk. It's broken into, this could be files, but there's going to be broken into pieces that are capable of being stored in memory in their entirety. And then those, we're going to be reasoning about these buckets when we do our actual breadth first search. Okay, and then if we can load them into memory, we're going to do some processing on what happens in memory. When we're done processing, we're going to write those states back out to disk, and we're going to continue to process here. Okay, so the big difference here is we're going to process, if we looked at the previous external memory search, we were processing individual states. And we're still going to process individual states, but like we process everything that was on disk was exactly a state that was either a duplicate that had to be removed or was a state that we were going to expand. Here we're going to process whole buckets where the buckets contain every state in the state space. And so some of these may be at previous layers, some of them may be at other layers, some of them we haven't seen yet, some of them we have. And now we're going to come up with algorithms that say, how do we deal with this? But the key idea is that we can load one into memory. It fits into main memory. We can do any operations we want while they fit in memory, and then we can write them back out to disk. So we're going to basically process the breadth first search one bucket at a time. Okay, so what does 2-bit breadth first search do? Here it's going to load a full bucket. And really this is, so 2-bit breadth first search is for all buckets. We're going to do this repeatedly. We're going to sort of think about how do we do get from one depth to the next depth. And here we're even going to think about how do I process one bucket at the previous depth and get it to the next depth. Okay, so I'm going to load a full bucket. And as I said before, what 2-bit breadth first search wants to do is minimize node expansions. So what we're going to do is we're going to expand all states. And for simplicity, we'll think about the 2-bit search. We'll think about in the current layer, what are the states that we're expanding right now? Okay, so we load a bucket. There's a bunch of states there. Some of them are previous layers. Some of them we haven't seen. You know, they're all in these different, you know, unseen next layer. Some of them are previously expanded. We're only going to take the ones that are in the current layer and we're going to expand those. So we're going to expand all those states. And what are we going to do? If the successors are in the current or in the same bucket, then we're going to write immediately. Okay. So what could happen here is I could have some state here, I generate a successor, and it goes back into the same bucket, and I can immediately update. So maybe it's this node that's been unseen, and now it's going to go generated. Maybe it's a previous layer, and I can just discard it. But the states that are expanded, because I've loaded this one bucket into memory, anything that falls inside here, I can process in memory immediately. So this is a little bit akin to the structure-based duplicate detection, because we do get the structure. There's some sort of structure here. And in fact, if my successors tend to be locally in memory, then I'm going to tend to get most of them to have their duplicates found almost immediately. So that's going to be good. I'm going to write or process them. They might be duplicates. And if they're not, we're going to write to scratch. That is, with every single bucket that we have up here, associated with that bucket is going to be another disk file here, which is all the states which are inside this bucket, but have yet to be processed yet. Okay, so we have the scratch file here, a temporary file. Now, if we think about this, all the stuff in memory, that's all just in memory, so that's going to be fine. This writing to scratch, we're just dumping to scratch, so it's just writing files out. Writing duplicate, or they may be duplicates, they may be new states. We don't care. We're just writing them to disk. And because we're writing big chunks just to disk sequentially, that's going to be a very fast, very efficient process. Okay, so this says load a bucket. In that bucket, we expand all the states in the current layer. The successors go into the same bucket, are going to be processed immediately. Otherwise, we're going to write it to scratch. And what we'll do here, as I said, there's a couple different ways this could be done. But we're going to say is, look, I've expanded this state. So now I can change that state to say, now it's been expanded. There's ways to avoid this in practice, but for simplicity, we're gonna say that we're now changing this state. So I've got this, and then when I'm done, I'm going to write bucket to disk. Okay, so that's a 2-bit breadth first search. As I said, it's really trying to minimize the number of expansions that are performed. And the reason why is it's expanding, so it's loading these states, it's expanding everything that is in the current layer. If the successors are in the same layer, then it's handling them immediately. Otherwise, it's writing them to a temporary file, which will later on be processed. So there's one other thing here that I need to add. Of course, we didn't know about that, so I didn't want to explain it yet. But what we're going to need to add here is, let's just move this down, is we're going to process the scratch file. Okay, so we have the file that was written in the previous layer. It's got all the states in it that potentially were written at the previous depth. And so I can take all those states and now I can process them. So this is when we process the file. And because I've processed it, then I get to do all the states at once instead of trying to load it and do them one at a time, which can be very inefficient. Okay, so 2-bit breadth first search then just does this over and over again. So this process we do for all buckets, and that gives us one, when we do it for all buckets, that gives us one pass through the tree, or through the breadth first search. And then I do this repeatedly for each depth of the search until all states are set, or until no states change. Maybe some states are unreachable, but that'll give me a full breadth first search. And some trade-offs here. Basically, 2-bit breadth first search is going to work really effectively when our successors tend to fall into the same bucket. Okay, so that's going to be really important. It's also going to work very well when the cost of performing an expansion is really high. If the number of expansions that I perform is really large or is very expensive, so like maybe I have it's just very expensive to see what the next operations are, then I don't want to do that many, many times. And then the other thing here is I have these temporary files. So this temporary file can get to be quite large. And so if my temporary files get too large, I have to stop my search and I have to clean up my temporary files and basically flush them into buckets into memory. And I can do that at any point. I can be taking my largest temporary files and be putting them back into the bucket in memory. But if I just summarize this, and I'll just put this here, the plus for this is it works well if I have locality of my successors. That is, they tend to fall in the same bucket. It works well when we have, let's see, yeah, so there's a locality of my successors when I have a small scratch files. And it works well when I have expensive expansion of states. And sort of course, if it works well when the scratch files are small, of course, it's not going to work well when we have large scratch files. We'll have to spend a lot of time going back, cleaning up scratch files, going back, cleaning up scratch files. And so what you notice here is that the design of this algorithm, it's designed to minimize node expansions because it expands these states exactly once. It writes their successors and says, okay, once I expand them, I must handle every successor immediately. And then I'm done with it. I'm never going to handle them again. And we're going to get another approach, which I'm going to just copy this figure to make it a little bit easier to see just down below, so I don't have to scroll up all the time. So we paste this here, and then I'll actually be able to draw on this figure. So now we're going to have WMBFS. Okay, so just to finish this off, now that I've got two separate figures here, also sitting on disk here is scratch files. And we have one of these per bucket. At least one per bucket. You might have more. Again, depending on your parallelism that you might want to get here. If we're handling these in parallel, then we might have different threads or things writing to different scratch buckets. But a minimum of one per bucket. Okay, so we're right minimizing breadth first search. What we're going to do here is we're going to do something a little bit differently. So right minimizing breadth first search basically says I don't care about expanding states multiple times. So what we're going to do is we're going to load. In fact, we're not even going to load. So let's just call, we're going to have a 1-bit representation in memory, E-M-O-R-Y, Okay, and what this is this is 1 bit per state. And what we notice here, so just to be clear, this representation here that was sitting in memory was storing whatever the value is of a 2-bit search, or if it was a modular representation, it's storing a modular representation. All of that is being loaded directly from disk into here, and the same representation sits in memory and in disk. And what we're going to have here instead is we're going to have a representation where what is here represents what is sitting on disk, but it doesn't actually correspond to what's being stored on disk. And what we're going to do is, and this may seem a little bit crazy the first time that you see it, but what we're going to do is we're going to actually go through all of memory. Okay, so we're going to have a 1-bit representation. We're going to read, oh, let's do this back in black, sorry. Okay, sorry, I wanted this. We're reading through memory here. So what we're going to do is we're going to read all states in memory. And this is for 1 bucket again, like we were doing it above. So we're going to read all states in memory. And we're going to expand all states that are in the current layer. Okay, and what we're going to do is we're going to mark the successors in memory. Okay, so what's going to happen? Let me just make this clear. So we read through memory here, and we're going to find some number of states that are at the current layer, whatever they happen to be. And for every state that we find at the current layer, we're going to expand that state. And if any of the successors of the state happen to be in what's sitting in memory right now, then I'm going to mark it. And I only need 1 bit per state. So one thing that we see here is because we only need 1 bit per state, the memory required to store a state is less than up here where we might need, at least 2 bits per state. If we're using a modular representation, we might want even more. Maybe we want 4 or 8 bits per state. But what I keep in memory is only 1 bit per state. So my buckets are going to be able to be larger in a right minimizing breadth first search. So I drew a whole bunch here, but maybe I'd have half or even a quarter as many buckets in a right minimizing breadth first search as I would in a 2-bit breadth first search, because I'm only keeping 1 bit per state that just says, was this state that I expanded, like I'm going to mark its successors and say, this state was a successor of a state at the current layer. I go through the entire state space and do this. And when I'm done, what I have here is a bit representation of all the states that possibly are states at the next layer. And then what we're going to do is we're going to merge the bit representation with disk. Okay, so the first step that I'm going to do, just to be clear here, one, we're going to read through all states in memory. We're going to write them into this piece of memory right here. And then, we're going to expand, of course. So number 2 might be, as I'm doing that, I'm going to expand, writing any successors into here. And then 3, what I'm going to do is I'm going to be flushing these back. I'm going to flush these back onto disk. So I'm going to read through here. And this is essentially where we're doing our duplicate detection. So any state that was a potential successor, as I go back through here, what I'm going to discover is, if we're looking at these values, well, if they're ungenerated, then their value becomes, oh, this is a node that's going to be in the next layer. If they're a state that's already been expanded, then I say, oh, it's already been expanded, I'm going to ignore it. Or if it's a previous layer, I'm going to ignore it. So basically what happens is we say, well, these are all the potential states in this bucket. And again, remember our buckets are much larger now because we're only using 1 bit per state. Here's all the potential states in this bucket that could be at the next step, and the ones that are at the next step, I'm going to write them to disk. And then we're going to repeat this for the next bucket. I'm going to expand every state in memory, and then I'm going to do this again and again and again. Okay, and so in what we see here is that we are going to read through all these states one time for every bucket. We're going to expand every state one time for every bucket. But what we're going to do here is we're only going to write this set of states one time. So what I'm saying here, what this is willing to do is this is, look, I'm willing to take my states and I'm willing to write them. I'm willing to read them many times, and I'm willing to expand them many times, but I'm only going to write these states to disk once. Okay. And by doing that, so if we think back about SSDs, this helps minimize the number of writes that you need to do in a solid state drive. But the other thing that you notice here is that we have no temporary files. So we had temporary files up here, these scratch files, and these scratch files can get quite large. And I didn't say it, but the scratch files are also stored with an explicit representation. We have to store the explicit state here, where we never have to do that here. So this actually can be as large as the entire disk that we have, and we'll still be able to store it here because we'll never need any additional scratch. So if we want to think about the pros and cons of this approach, so it's going to work really well if there's fast state expansion. It's going to work really well if we have few buckets. And it's going to work well if I have a large state space. That is, I don't have much room for storing lots of buckets or lots of scratch files. If I can only afford to store the state space, I don't ever have to worry about having extra memory for scratch files, which can get very large. But it's not necessarily going to work well if I have if I need many buckets, because I'll have to go through the state space many times, and the locality doesn't really matter so much here. It's going to the locality is mostly going to be handled. Many buckets or expensive state expansions. Okay. And so if I have, again, so if I have these properties, then I'd be probably better doing a 2-bit breadth first search. If I have these properties, I'm better doing a write minimizing breadth first search. But what we can see here, which is sort of most important, is there's sort of trade-offs in the way that we do our search. That is, we can think about, I immediately am doing a lot of duplicate detection here by storing the states that have changed in memory, and then I write them at one time. So this is thinking immediately about trying to remove duplicates, and therefore I don't have to store them all on disk for later on. And then when I write, I do the rest of my duplicate detection. But I have to go through the state space like as many times as I have buckets. So this picture here of having many, many buckets is not a picture where we're going to want to use write minimizing breadth first search. On the other hand, 2-bit breadth first search, I do need these expensive scratch files here. And here I'm loading exactly the representation of a bucket into memory. And so there's a trade-off there of like my buckets have to be smaller so that they can actually fit in memory so that I can store them there. And then here, this is where the duplicate detection, some of the duplicate detection is happening here, but some of it is happening from the scratch files, both within the scratch file and as a scratch file is being written to memory. And if you think about this, this is a hash-based duplicate detection. All the hash files go inside here. This is my hash table, and then I write them all into here, and I get my duplicates as I do that. This is also basically hash-based because I get my hash inside here, and I'm finding my set of duplicates there, and then I'm also getting them as I write back there. So these are two ends of a spectrum on ways that we can do external memory search. And in practice, you could probably do something in between. Nobody's proposed to do hybrids between these, but you can see this question of sort of what is most important. Is the most important thing to only be expanding every state once? And if that is, then the 2-bit breadth first search is going to be the way that is going to minimize my node expansions. Only expand a state once, keep track of every state inside these scratch files. The write minimizing breadth first search says I'm willing to expand states many times. And so if I can afford to do this, then this is much more effective. And just to say, I haven't been talking about exact numerical results, but if you look at a state space like the Rubik's Cube for building large Rubik's Cube pattern databases, that the right minimizing breadth first search is much more effective for the Rubik's Cube, where it's fairly inexpensive to generate successors. We have 18 successors in the Rubik's Cube, so we don't tend to have the locality that you want to see. We see lots of states going to scratch in Rubik's Cube. And so it tends to work much faster there. Where if you looked at something more like the sliding tile puzzle, where the blank doesn't move very much in each turn, then something like a 2-bit breadth first search can be very effective for those types of state spaces. So that being said, these are 2 example algorithms for doing external memory search. And we can see sort of the contrast, but there's some key ideas of using buckets to divide up the state space, loading something that represents that bucket into memory and processing on that portion that fits in memory, and then writing that back out, which is in common to both of these. And then we can choose our underlying representation, whether we're just thinking about processing through, unseen, next, current, or previous, or are we actually trying to get depth stored here by using some sort of modular representation. And again, and didn't talk about the full details here. You'll have to go back and look at those papers. But this concludes. We did one very, very fast lecture on external memory search. We're going to talk more about how we can compress some things related to this and how these relate to building heuristics a little bit later in the course. So we'll stop here for today.